Good morning, class. So today what we're going to do is take a little bit of time and talk about a review. I'm going to try to take about a half hour, maybe 45 minutes to cover some of the big things that I think you probably need to be paying attention to. So what we'll have here in the beginning is the following information. So chapters you need to worry about. Chapters 4, Chapter 5, Chapter 6. Also got to review AWT. That is that graphics package. You also need to worry about extended number systems. You also need to worry about and review extended gates. Right? So, Chapter 4 in general that's all about how do we digitize stuff. So if you remember some of the big things that we need to worry about when it comes to digitization, we need to worry about quantification and sampling. So the first thing we do in general is sample, and the next thing we do is we quantify. So for example, let's say that we have a photo, and our photo is 1080 by let's do this right. So 1920 by 1080. All right. So that's actually an HD source. That's actually 1080p. And if we took and we figured out what our samples are, the samples in this case are the pixels. All right. From the real world, we've sampled 1920 by 1080 pixels. And then the next thing we need to know is at what level are we going to quantify and what are we quantifying. So if you remember, we're quantifying RGB. That's red, green, blue. And it'll be 8 bits per channel. So 8 bits for red, 8 bits for green, 8 bits for blue. So for us to be able to figure out first how many megapixel camera this is, we would simply multiply 1920, the width, by 1080, and that's going to give us the amount of information. So let's have a quick look at that. Oh, it's on the wrong screen. There we go. So 1920 by 1080. Let's try that again. 1920 by, try it again. 1920 by 1080 equals, that's about a 2 megapixel camera. All right. Now, the next thing we're going to do is we're going to take and we want to figure out how much storage space this actually occupies. So if each one is 8 bits, each pixel is 8 bits, that's 24 bits per pixel, BPP. So 1920 by 1080 by 24. If I multiply that out, that gives me 497,66400, and that's going to be in bits. So, next thing we need to do is we need to take that particular number and we need to figure out what that is in bytes. So to do that, and I'll let you do this on your own. You're going to take that large number, 497,666,400, 49,766,400 bits per photo, right? You divide that by 8 to give us bytes. You divide that by 1024 to give me kilobytes. Divide that by 1024, and that's going to give me megabytes. So if I do what I just suggested, I'm going to divide by 8, divide by 1024, divide by 1024, and if I got it right, let's try it again. 1920 by 1080 times 24 divided by 8 divided by 1024 to give me kilobytes, divided by 1024 to give me megabytes. We should wind up with about 5.9 megabytes per photo. All right. Now that's without compression. Right? So that's no compression. So if I were to compress this, running along the same vein, if I were to take and compress this, and let's say that I did, well, I don't know, a 10-to-1 compression ratio. That means that I would take this, and now it would be 0.59 megabytes in size with the 10-to-1 compression ratio. All right? Now, the next thing we have, let me have a look back here, kind of keep that off to the side. The next thing that we need to think about is how do we generally do that. We can do that for anything. We can do it for audio. When we audio, what do we do audio? What are we sampling? We're sampling amplitude. When we do video, we're sampling frames, and then inside of those frames, each one of those frames is actually a photo. We can do that for characters, you know, thinking back to ASCII and Unicode and so on and so forth. And the list can go on and on and on. One of the big things to remember is we're always in base 2. All right. So when I ask you anything about combinatorics, when I ask you how many combinations there are, base 2. And then you ask yourself, well, how many things are there? Meaning, how big is something? So if I say something is 16 bits wide, it's going to be 2 to the 16th. That's going to give you 65,536 different combinations. When you think about RGB, for example, and I tell you that R is 8 bits, G is 8 bits, B is 8 bits, 2 to the 8th is 256, right? I'm sorry, 2 to the 8th is 256. So that means there's 256 different quantifications per channel, except for total we have 24 bits. So you figure out what 2 to the 24th is, and that's how many different color combinations we have with an RGB color space. All right. I can go on and on. Like I said, the more bits we have, it tells us the more clarity that we're going to have, the better resolution we're going to have. Other things can kind of dictate that as well. The number of samples that we take, the more samples that we take, is going to dictate the more clarity that we have. So when it comes to digitization, to sum this up, don't forget that it comes down to two different things. It comes down to the sample that we take, and then it is also the quantification level that we use. All right. Now, the next thing is going to be the different gates that we have. Now, the book talks about a NOT gate, also remembering where all of this stuff comes from, right? So it originally comes from a transistor, and I'll let you look back at your notes to think about how that actually works. What's the emitter, so on and so forth. What's the base? So a NOT gate, you know, it's going to look like that. A AND gate is going to look like this. An OR gate is going to look like this. A NOR gate is going to be a not OR gate, so it's going to look just like a NOR gate except for there'll be a circle on the end. And then we're going to have an exclusive OR gate, and then we're going to have a NAND gate, right? And then, so I should write these in for you. And then the other thing to remember is for each one of these, you need to write out the Boolean and the truth table. Now, I didn't do that, but you have all of this in your notes, and you're going to want to memorize this stuff. So, especially for the exclusive OR, that's one of the ones that is tricky. So, if I have two inputs, A and B, how many different combinations do I need to worry about? Well, 0, 0, 0, 1, 1, 0, and 1, 1. There's 4, because remember, two inputs, right? And each input can be a 1 or a 0, so that's base 2. So 2 inputs, 2 to the 2 equals 4. If I had 3 inputs, that would be 2 to the 3rd. If I had 4 inputs, that would be 2 to the 4th, so on and so forth. All right. So keep all of these things in mind as you move through. Studying with all of this stuff. So let's do maybe a really brief combination circuit. Let's say that we had something like this. We have a couple of inputs, A, B, and C, and those are going into an exclusive OR, and maybe an AND gate, and then maybe those are coming out and into an OR gate. Okay, so that's an exclusive OR, this is an and this is a just an OR. And we'll have A and B coming into that one, and B and C coming into that one. So how do we go about solving X? And X is going to be what my Boolean is overall in my output. So we begin left to right, top to bottom. So I'm going to take, hopefully, let me see if I can get just a little bit more there. There we go. So I want to begin with A, B, and C. So I have 3 inputs. So you got to ask yourself, well, how many different combinations do I have? The answer is 2 to the 3rd is 8. Always start at the top, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. We move left to right, top to bottom, so the first one I come to is the exclusive OR gate. An exclusive OR gate says that there has to be both states present. So I'm going to write this out as A exclusive OR B. So I'm going to look at the A column and the B column, and I want to say that's going to be a 0, 0, 1, 1, 1, 1, 1, 0, 0. All right. The next one I have is an AND gate, so I've satisfied that one. So I want to say B and C. So I'm going to look at the B and the C columns. I'm going to AND those together. So 0, 0, 0, 1, 0, 0, 0, 1. All right. So those are the A and the B ANDed together. Then I'm going to move on. So I've done that one. So check on that one. And I'm going to OR together the output of the exclusive OR and the output of the AND. So it's going to say A exclusive OR B, ORed to B and C. So I'm going to OR those guys together. I say 0, 0, 1, 1. Somehow I got an extra 1 in there. 1, 1, 0, 1. All right. So if I were to wire this up in Digital Works, that should be the output unless I messed up right in here somewhere. But we'll come back to that later. This is the most important stuff that you need to remember is these 6 gates. You need to make sure that you have all that memorized, the truth tables, and what the Boolean logic is. And I think you're going to be pretty good if you do that. If you do that. All right. So what do we have next? Well, those are some of the bigger points for it. So let's move on to maybe AWT. So we'll take a break from Chapter 4 because that was all Chapter 4 stuff. And in AWT, you want to keep in mind that as you draw a particular frame, remember, you're not going to have to program anything for this. I don't have enough time. But you got to remember, where's the 0, 0 coordinate, right? Remember, it's an X and a Y. So if this were a frame that is, say, 1,000 by 500, that means that it's 1,000 wide by 500 high, right? So if I were to ask you where the 0, 0 coordinate is, you're going to remember that it's right there. Once I have the 0, 0 coordinate, it's pretty straightforward to be able to label the other corners on this. All right, so 0, 0 is the upper left-hand corner. It's 1,000 by 500 wide, so that means that this particular corner is going to be 1,000, 0. It means this one is going to be 0, 500. It means that this one is going to be 1,000, 500. All right, pretty straightforward on AWT. So the next thing we would want to remember is, let's say that I asked you to place a circle into this at the, say, 500 by 250, all right, wherever that coordinate is. So that would be the X and the Y. And then the next thing I would do is give you, say, I want it to be 100 by 100. Keep in mind what's going to happen. So in this case, it's going to start right here. It's going to have an imaginary block that would be 100 by 100. It would fill in a circle, and that's where my circle would appear. And you can go into your own stuff and test that out and see if that actually is how it works. I think you'll find that it is. So the next thing that we have up is Chapter 5. And let me see what some of the big points are out of Chapter 5. I'm going to go into the book for this. It might take me a second to pull this up. Okay, so here's Chapter 5. Some of the big things that you want to maybe remember in this chapter. I'll kind of go on and walk through here with you. Get that rid of that. There we go. So, whoops, sorry about that. So as we move through here, it starts talking about memory. You know, you have all these different things such as the ALU, the CU that are inside of that central processing unit, and your memory and your output are going to be connecting to that. It does talk about specifics of memory and how one memory cell is 1 bit, and how your MAR, your memory address register, and your memory data register work with that memory. We talked for about 2 weeks on this particular class. We went through, and there's a lot of other things. We talked about the size of things, how big things actually are. We went through that exercise of growing up all the way through yottabytes with this stuff. There it talks about the MAR and the MDR. Drilling down even further into memory cells. I know I'm kind of moving fast through this. We talked about cache. We talked about how that's ultra high speed memory. It tries to do forecasting. There's algorithms that try to do forecasting. And it's short-term memory. We talked about, if we're not to it yet, we talked about the principle of locality. We did talk about mass storage in the form of hard drives and solid state drives. We talked about how CDs and compact discs work. We talked a little bit about how magnetic hard drives work, where you have the concentric rings, which are known as tracks. I even passed that stuff around. Here it does talk about seek time, latency, and transfer. I'm not going to ask you that explicitly on this, but you should probably have a basic understanding what that is. Other things that we did, although that stuff would be fun, we talked about the arithmetic logic unit, what the arithmetic logic unit does, what are the purposes of registers, and we went into talking about control unit. Now it's responsible for keeping track of all of the different instructions where we are in the execution of a particular program. We did talk about opcodes, the importance of understanding opcodes. What's the difference between a RISC, and a CISC computer? RISC, reduced instruction set computing, CISC, complex, right? We did not go into how do we load, store. We didn't do any of the assembly for this. I wish I had time to do it, but I don't always have the time to be able to get this stuff done. And there's the overview of everything, how everything is kind of touching together. You know, there's one thing that I really didn't mention that I should do that right now. Let me pull this back up here for you. So when we think about a CPU, there are several really big things that it does. We have these things called clock cycles. And we have machine cycles. All right. Clock cycles, those are when you hear somebody say, well, I have a 4 gigahertz CPU. That means that the CPU is able to do 4 billion calculations, if you will, per second, but it's the number of times that it's able to refresh the state of a register or a cache or something else. All right, those are the clock cycles. Machine cycles are a little bit different. Machine cycles are made up of 4 clock cycles. All right, so with that being said, there's something very specific that happens with these clock cycles. The first thing that happens, and one of the things that is in this machine cycle, the first thing that happens is we fetch. What do we fetch? An opcode. The next thing we do is we decode. So we decode. What are we going to decode? The opcode. The next thing we're going to do is we're going to execute the opcode. And finally, we're going to store the results of the opcode. So these 4 items make up a machine cycle. So I need you to think of it this way. If you have a 4 gigahertz CPU, how many machine cycles is it capable of? Well, the answer is 1 billion. All right. It can do 1 billion machine cycles per second, meaning fetch, decode, execute, store. Now again, this would be like if we had a Unicode, or sorry, a Unicore CPU. If we had a quad core, for every clock cycle, it should be able to do for every 4 clock cycles, it should be able to do 4 machine cycles, 1 for each core. And that's how things start getting faster and faster. Now we have other things that I won't get into too much, but we have this thing called pipelining. And then of course the cache, that really helps out as well. Okay, so let's flip back over here to the book and have a look at that. Some of the other things that we have here. There it goes into megahertz, gigahertz, MIPS, and gigaflops, floating operations per second. Here is talking about this thing called Moore's Law. It starts getting into Moore's Law. And what Moore's Law states, and it was this guy named Gordon Moore from Intel. And what he said was that over time, density of CPU, or of transistors, which also equates to speed at which they can perform, will double every 18 months. Or the technology will it'll be half in price. Now we don't see that as much because this was the projection, right? It was a linear growth, and what has happened is it begins to kind of fall off, and we don't have that. That's where the quad cores, the 6 cores, the 8 cores, that's the only way they can keep up with Moore's Law at this point in time. And all it really was a statement. It was an observation. It wasn't an actual law that he came up with that said, oh, this is the way that it has to be. It was an observation that he saw, and it was an observation that held true for a very long time. But it's starting to fall apart, so we have to eke out other efficiencies in our CPUs. All right, so we'll keep on moving here. Talks about signaling. If you haven't read this, by the way, you should probably read it because there will be things on there that that I'm not covering currently. All right, so that pretty much kind of rounds it out. You might want to read this thing about quantum computing. I did talk about that a little bit, and it's just kind of neat to see. So the last chapter that we're going to have is the chapter 6. And in chapter 6, whoops, I somehow jumped ahead. There we go. I don't know how I got all the way up there. Didn't mean to do that. So chapter 6, really, the bulk of chapter 6 is operating systems. That's the biggest thing that I want you to remember. I want you to remember all the different components that make up an operating system and what the big parts are for an operating system. For example, it's supposed to detect and prevent deadlock. What deadlock is when there's a particular resource, let's say a video card, all right, and you have 2 processes that are trying to grab a hold of that particular resource at the same time. If both of them actually grab a hold of it, neither one of them can use it. So the operating system has to step in and say, you're not allowed to use this right now. Process 102, PID is what that would be called, process identification. PID 102, you're blocked from using it. 101, you go ahead and use it. So the operating system, using scheduling algorithms and other different things in its arsenal of tools to detect and prevent deadlock, steps in and says, 101, you're allowed to use it. 102, you're not. You'll be able to use it next. All right? So that's that whole idea of deadlock. But then in the book, it starts getting into a whole other set of things that the operating system does. For example, it handles security. It handles memory management. It handles access control, ACL, access control lists. That kind of goes back to the security. It handles file systems. Remember we talked about NTFS, FAT32, FAT32, not 30, 32, etc. Whole bunch of other things. Let me see what else we have in here. To refresh my own memory, it talks about schedulers. And that kind of relates back to this whole idea of deadlock. The schedulers handle that. The different utilities, it talks about garbage collection through memory managers, right there. It does talk about, you know, an operating system. So keep this in mind. Back when a computer was just a bunch of circuitry, you actually had an operator. This was a human being, and you had a loader. All right. So the loader would carry over the program. Here's my wonderful art, right? He would carry over the program and he would load it into the computer. The operator would start running, and it would be multiple operators would start running the computer, and then on the other end would out come the result. Well, eventually somebody said that is awfully expensive for us to have a human being doing the loading and an operator doing the operation. So that's where the operating system came from, and all the different components that make up an operating system all stem back to actual human beings that used to perform these different system software operations. I don't think that I have much of anything else. You do want to read and review. There will be about, let's see here. As you look at things, I think I covered everything. Double check. Yep. AWT, number systems, gates, chapter 4, 5, and 6. All right. So as you study for this, you need to remember that about 85% of this is going to come from your notes. All right. If I talked about it in class, that means it's probably going to wind up on that exam. And that leaves about 15% that's going to come from the readings. All right. Now remember, I only have 50 minutes in which to give you this exam. That is it. So there may be a problem like this, right? But there's not going to be 5 problems like that. Oh yeah, I did forget to mention, you're going to have to be able to, in number systems, I don't think I really did that. Let's do a couple of problems here. Let's say that you have to add together 2 hex values, FA plus BAC. All right, so that's a hexadecimal problem. You're not going to have a lot of these because you have 50 minutes. That's it. But you also can't use a calculator on this. You would be allowed to use a calculator on this. All right, and I'll specify it. Usually the way I do it is there's 2 parts to the exam. You do the first part without a calculator, and then you come up and use the second part with a calculator. So let's go over this. You get a problem like this, you can't use a calculator, you can't do it in your head, so make sure you write out that cheat sheet. So 0, 1, 2, 3, 4, 5, 6, 7, B, C, D, F. Yep. Then I'm going to start over. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. All right, here we go. So A plus C. I'm going to start at the C. I need to remember that I can remember how many place values this is worth. All right. So I want to start at the C because it's higher, and I'm going to count up A places, which is 10. All right. So C, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a 16. 6 with a carry of 1. F plus 1 is 10. Plus A is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1A. A with a carry of 1. A plus 1 is B plus B. So B plus 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16. 6 with a carry 1. F plus 1. F plus 1 is a 1, 0, so 1, 0. So 106A6. And you know what you can do? You can take that calculator, whatever I did with my calculator. Let me see what I did with it here. I'll pull up my calculator again. I am now going to kick my calculator into programmer mode. So there I am in programmer mode. Now I'm going to kick it into base 16. And I'm going to say, notice how everything shows up. So FA plus BAC 106A6, and that is exactly what I came up with right there. So let's try another one. Let's try an octal addition. Let's try 16832 plus 57631. Now as you begin this, you need to always ask yourself, what is the range? And what are the digits that are in there? Well, the range is 0 through 7, and there are 8. All right, 0 through 7. Oh, wait a second. I can't do that one. All right, and you would write can't do. Let's try it again. 765 plus 321. All right. Again, I'm going to write out my cheat sheet. 0, 1, 2, 3, 4, 5, 6, 7. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. 5 plus 1. 5 plus 1 is 6. You want to get these points. Take your time. 6 plus 2. 6. 1, 2, 1, 0. 0 with a carry 1. 7 plus 1 is 1, 0 plus 3. 1, 2, 3. 1, 3. 3 with a carry 1, and I bring it down, and there's my answer. You can't double check these on the exam with a calculator, but you certainly can as you set up your own practice problems. So I want to say, I want to kick it into octal, 8, and I want to say 765 plus 321, 1306. So I'm correct with that. All right. All right. The last one would be binary, right? Binary, number of digits. Well, that is going to be 0 to 1. And I'm sorry, number of digits 2, and the range is 0 to 1. So 1, 1, 0, 1 plus 1, 1, 1, 1. 1 plus 1 is a 0 with a carry of 1. 1 plus 0 is 1, plus 1 is a 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 with a carry of 1, and bring it down. Don't believe me? Want to double check it? Let's see, I don't know how to do it actually on this. Oh, here we go. It's going to show me right here in my binary. Let's try this out. I don't know that I can do it with this particular calculator. Let me see. Scientific is going to give me a binary. 8, 10, 16, Unicode, ASCII. Windows has it. I can't figure out how to do it here, and I'm not going to take the time to keep playing with it, but I assure you that that is correct. And I just learned a limitation of this particular calculator. You could take, if you wanted, you could convert that into a hexadecimal number. So watch this. So I could take, and I could say 1101. And so that's 8 plus 4, 8, 9, 10, 11, 12, 13. So what's a 13? That's a D. And this is an F. So we can say D plus F. So D plus F. And if you notice right here in the binary, 11100. Whoops, sorry. 11100. So if you look right here, I added those two together. It would be a 1C, and if you look right here, it says 11100, just like our answer was. All right? Okay, So with all that being said, there's a whole bunch of other things that I could do. It's going to be the exact same thing over and over. So don't get discouraged if you come up against a problem and you're like, wait a second, we didn't cover that. I assure you we did cover that. All right. It's just it might be the problem is in a different way than what you're used to thinking. So take your time, work your way through it. You have 50 minutes. All right. And I'll probably even give you an extra 5, but you have 50 minutes to be able to complete the exam. So don't worry about it. If you have any questions, you can feel free to email me over the weekend or today. I'm actually in here at work right now doing a few things, so I'll be answering emails until probably about 12 or 1 o'clock, and then I'll take a break until later tonight. Have a great day.